Hello everybody, hope you're doing well. This is paper 2 from November 2023 and this is time zone 1. Now let's have a look at it and see what we can do. Okay, first question is a 12-mark question. Let's read it. Jan is investigating the shape of model helicopter propeller blades. A cross-section of one of the blades is shown, graphed on the coordinate axes. The shaded part of the cross-section is the area between the x-axis and the curve with equation y is equal to 4 root x minus x over 2 plus 1. And we have this given domain right here where they're saying for certain inputs where x is greater than 0 and less than 64. So what are these variables? X is the distance in millimeters from the edge of the blade, and y is the height in millimeters above the horizontal axis through the blade, as shown in the diagram. So what we have here is we have some function which takes x values, or our distance from or on the horizontal, and when we substitute or input these x values, we get a corresponding y value, or a height of a propeller blade, as a function of our distance along the horizontal. So let's go ahead and see what they're asking us for the first part. The first part, part A, they're asking us to find the values of A, B, and C shown in the table. So we're asked to find A, B, and C right here. And these are all y values. So in this case, if we have an x value, an input, it looks like we should be able to just input these values into our function and then find the corresponding y value. So this looks to be, at the very beginning, a more straightforward input-output question. So, to find the value of A, let's input the value of 16 into our function, for example, and then we'll do the same thing for 32 and 48. Okay, so let's go to the calculator and work out these values. Okay, so we have a function for square root. Our first value is 16. Minus, we'll get a fraction here. This is going to be 16 over 2, and then it's going to be plus 1. Okay, since we're here, let's do the other two as well. This is going to be 4 square root 32 minus, once again, 32 over 2 plus 1. And then the last value was 48, so let's go ahead and input that. 4 square root 48 minus 48 over 2 plus 1. Okay, so here we go. We have values for A, B, and C. Let's go back to the document and write these out. So for A, the value was 9. For B, the value was 7.627, so we're going to round that to 7.63. And for C, we had a value of 4.712, so let's round that to 4.71. Alright, not a bad 3-mark question to start. If we wanted to, we could put millimeters, but just the value should be fine as well. Okay. We're then told that Jan uses the trapezoidal rule with 4 intervals to estimate the shaded area of the cross-section of the blade. Find Jan's estimate of the shaded area of the cross-section. So in this case, remember, often IB questions won't ask you to perform some kind of calculation just to test a discrete scale. Often we'll have a question that will lead to something else. So here they're asking us to find these heights at different points. That is to say at 16, 32, and 48. Actually, I'll do this a little better. 16, 32, and 48. To essentially divide up this horizontal section of this blade into 4 equal intervals. And then what we're going to do is apply the trapezoid rule. So what can we do? I guess we can first off apply the trapezoid rule, and then we'll give some background. There are potentially 2 ways to solve this. The first is the trapezoid rule, and then the second is using intuition and just finding the areas of the trapezoids themselves. So let's go ahead and use the trapezoid rule for the first part. So let's go to the formula booklet and find the trapezoid rule. This would be under calculus, so topic 5. All right. Topic 5, there we have it, 5.8, the trapezoid rule, and here it is. We'll take this and actually we'll work with this on the other page and unpack what is actually going on and what this means and how we can use it. All right, so let's go down and write it here. So this is part B, and the trapezoid rule is given by, we're asked to find the sum of some function from some starting point to some end point, and then it's some function, and then the variable is x, so we just write it in terms of dx. And then this doesn't give us, the trapezoid rule doesn't give us the exact area, it's just an estimation. So we write these approximately equal to. And then we have our trapezoid rule. And it's 1/2 h, and we'll talk about what h is in a sec. Then we open up some brackets, and we have y0 plus yn, or y0 plus yn. And this would be the first vertical height, and this would be the vertical height at our endpoint. So vertical height at the start, and we can have the vertical height at the end. Maybe we'll label that. So we'll say y at start, and this would be the y value at the end. The nth is the very end. And then we have plus 2 times, and this will be y1 plus y2 plus all the values in between, all the way up to yn minus 1, which means the second last, essentially. So this would be the second last vertical height. Second last vertical height right here. And we also have this value of h. H essentially corresponds to, and this is actually maybe the better way to work out h, potentially. H corresponds to the size of our intervals. So we know this person, Jan, is going to divide this trapezoid, or sorry, they're going to divide this total area into 4 equal intervals. So how are they going to divide it? They're going to divide it into 4 equal sections, 1, 2, 3, 4, and h is the size of each of those intervals. So if we're going from 64, or from 0 to 64, our formula for h is equal to b minus a. Remember where we said in our original function, b was the endpoint, a was the starting point. B minus a over n. N is the number of intervals. It might be easier to think of this just in terms of intuition, as in b is our endpoint, a is our starting point, and just imagine, okay, what's the total distance that we need to travel? Well, if we're going all the way from 0 to 64, we travel a distance of 64, and we want to break that up into 4 equal intervals. So 64 over 4 is 16. So that means that the size of each of these intervals is 16 each. And that's going to be the value of h that our trapezoid rule takes. All right, so let's flesh this out a little more. So a was our starting point, b was our end point. We don't actually need these for our trapezoid rule, but this is just an intuition or idea of what we're kind of solving for. The sum under the curve, or the area under the curve. So 1/2 h, the size of these intervals, 16, and the y value at the start, so the height right at the very, very start. And when we're at 0, our height is equal to 1. So let's go put that in our formula. 1 plus, and this value right here was the height at the very end, or the y value at the end. And we said 64. 64 has a height of 1, and that's given to us right here at the bottom. Plus 2 times, and these are all of the intermediate heights. So we can write that, I suppose. These are the intermediate values for the heights at these given positions. So y1, they asked us to find this earlier. So when we're at the value of 16, what's the value? I'll use a different color, I suppose. When we're at the value of 16, what is our height? when we're at 32, what's the height? And when we're at 48, what is the height of the trapezoid? We found these values earlier, so we'll plug those in as well. 2 times, and this is going to be 9.00 plus 7.63. And I believe this last one was 4.31. So these are the intermediate values. So this was at 16, 32, and 48. 4.71. 4.71. There we go. And we can close our brackets. And just be mindful when you do plug this into the calculator, we have 1/2 times 16, so it's 8, I suppose, times all of this business. So make sure that you have brackets enclosing all of this, because we want to multiply this by 8 in this case. All right, so let's go to the calculator and work this out. All right, gonna get a new screen, and let's plug this in. So I'm gonna write it exactly as it is. This is going to be 1/2 times 8. And then let's open up a double bracket because we want to multiply everything. And this was 1 plus 1. And I'd actually encourage you to simplify some of this within these brackets beforehand and then just multiply this, or this should be 16 rather, our interval, the size of our intervals, and then multiply it by what's on the outside. So 1 plus 1 plus 2 times, and we had 9 plus 7.63 plus 4.71. All right, we want to make sure that this is multiplied by everything, so we've got this bracket right here, enclosing everything, and there we go. 357.44. Is that correct? 1 plus 1, that's good. Plus 2 times 9 plus 7.63 plus 4.71 multiplied by 8. This looks good. All right, so going back to our document, we know that the area is approximately equal to 357.44, or to 3 significant figures, 357, I think it's centimeters squared. This is just a model. Where is it? Millimeters. Millimeters squared. IB doesn't really assess units, or if it's not stated, they won't. Sometimes they'll ask you to. And units do come in, they are important when you're asked to convert, but generally when stating your answer, you can just write the value itself. All right, so that's the trapezoid rule. Here's the explanation of the trapezoid rule, and you can always use this approach as well if plugging into the formula is a little confusing. So when we're talking about a trapezoid, we have something like this. I'll try to write it in the corner right here. So trapezoids usually are represented flat, kind of on the base. And then this would be one parallel side, this would be the other. We would call this A and B, and then this would be the height of the trapezoid. What we're doing when we're using the trapezoid rule, we're rotating this trapezoid on its side. And let's put this a little closer. And we have that exact same trapezoid, but in this case, if we're rotating at 90 degrees, the height here is H, this long side is B, and this is A. And the area of a trapezoid, if we're looking at A and B here, is just going to be the average of these two parallel side lengths. So A plus B over 2, the average of them, and then multiplied by the height. And so, if we're trying to use the trapezoid rule, what we're doing, in essence, is we are making an approximation of the area under the curve using trapezoids. So if this is our first, let's say, segment, or if we want to have 4 intervals, we have one trapezoid with a height of 1, and then a height of 9, we said. And then we have another trapezoid. When it's 32, our height is 7.63. And then another trapezoid. Let's actually put that in, 7.63. And then we have another trapezoid at 48, which is 4.71. And then finally, one more trapezoid all the way here Again, with this height, since we are flipping it on its side with a height of 16. So h is actually the same throughout. It's the base once we flip it, but if we imagine our trapezoid on its side, it's the original height. And so we can use the trapezoid to find, let's say, the area of this, which is just going to be 1 plus 9 over 2 times 16. And this would be 9 plus 7.63 over 2 times 16. And this would be the average of these two, 7.63 plus 4.71 over 2 times 16. And this last one, running out of space a little, 4.71 plus 1 over 2 times 16. And if you were to add each of these up, so this plus this plus this plus this one over here, you would get that same 357. It just takes a little longer. All the formula is that condensed, where this is the size of the intervals. So our size of the intervals right here, traveling a distance of 64, breaking it up into 4 pieces. This is the height at the beginning. This is the height at the end. You see in our original trapezoid rule, we just had this multiplied by, we only had this as part of one trapezoid, and the end point is also just part of one trapezoid. And then we have 2 times, and then these intermediate values, these intermediate heights. And you see we actually have this as part of one trapezoid, and then it's also part of this trapezoid. So we multiply it by 2, and this we multiply by 2, and this we multiply by 2. So those intermediate heights. So there's really 2 different ways we could use the trapezoid rule in some sense. We can use the formula, or essentially we could find the area of each of the individual trapezoids and then add them all together. So A1, A2, A3, A4, and so on. A1, A2, A3, and A4. Alright, so once you become familiar with the trapezoid rule, it's not all that bad, and to be honest, these kind of questions, they do have a similar structure. I think you'll see another one on an earlier paper where they have the same structure. Use the trapezoid rule, and then it'll be followed up by find the actual area under the curve, and then how accurate is this estimate. Use the calculate the percentage error. Alright, so find Jan's estimate for the area of the cross-section. We did that. Now part C, write down the integral that Jan can use to find the exact area of the shaded part of the cross-section. So we want to write an integral. That means we're talking about our sum of the area under the curve. So the sum of some function that we can use to find the exact area of the shaded part. Alright, so this is C1. So this is our integral essentially up here. And it might look a little intimidating, but let's work it out. So this we can think of as the sum. And then we have our starting points and our ending points. So this is the start, this is the end, and then we have our function. And then in the IB, in AISL, it's always in terms of dx, but really you just want these to match. And so this thing right here, this f of x, is just our function, the thing we want to find the area under. So let's go write that out and fill in the blanks. I'm going to move this just a little. That's fine actually. So if we want to find the area under the curve, we know we started at 0. That was our starting point right here. And our ending point, we went all the way to 64. So 0 to 64. And what was our function? Our original function was 4 root x minus x over 2, I believe, minus x over 2 plus 1, and then we want to write this in terms of dx. And that's it. That's our area, or that's our integral for the area under the curve. Okay, hence use your graphic display calculator to find the area of the shaded part of the cross-section. Give your answer correct to 1 decimal place. Okay, so that's important. Be an unfortunate way to lose a mark. Let's take a look. So we've got the integral. Let's go to the calculator screen and work this out. Alright, let's get a new calculator screen. So in this case, we want to go Menu, Calculus, and we want to find the numerical integral. And here we go. We're starting at 0, going up to 64, and we want to find the sum. That is to say, the area under the curve of this function, which is defined as 4 root x minus x over 2 plus 1. And then we want to match this variable, so it's in terms of dx. All right, 405.333. So let's go back to the document and let's write this out. So what is the area under the curve? It's equal to 405.333. They asked us to write it to one decimal place, so just 405.3. Okay. All right. This looks good so far. So let's keep going and let's see what we can do. Calculate the percentage error of Jan's estimate or Jan's estimate, I'm not sure. Jan's estimate in part B. Okay. So this is part 2, I suppose, part 2 and 3. Here we have D. So percentage error, find the percentage error. This is actually given to us in the formula booklet as well. So let's go back and have a look. This is right actually at the beginning of the formula booklet. Under number and algebra, I believe. Sorry, I edited this up from earlier. Here we go. Under number and algebra, we have 1.6 percentage error. Right at the bottom, percentage error is equal to estimate minus exact over estimate times 100%. So let's go back. We'll write it out and explain what's going on. So we have percentage error is equal to, and then we have these absolute value signs. I'm actually going to write it out in words. Estimate minus exact over exact. And then we want to write this as a percentage because it's percentage error. And what these things, they're called absolute values. What they do is they say no negatives. So even if you get a negative value, we don't want any negatives. We want to write it just as a positive difference. We want to find what's called the magnitude of the difference between our estimate and our exact. So percentage error is equal to, our estimate was 357, our exact value was 405.3, and we want to say what fraction is that out of our exact value. We want to times it by 100%. Okay, so let's go back to the calculator screen and work this out. Okay, so we can use absolute value if we wanted to, but let's just write it out, and if there's a negative, we'll ignore the negative. So here we go. Let's write it out. We can write it out as one big fraction, I suppose. 357 minus 405.3 over 405.3. And this actually is going to give us as a negative. It's giving us to us as a decimal. Let's multiply by 100. And we'll press enter here. And so we have 11.9%. Remember, we don't want any negatives. The absolute value takes away the negative for us. We don't want to deal with any kind of negatives. So we just have 11.9%. Okay, let's go back to the document. Here we go. Percentage error is just going to be, let's write this as 11.9%. Okay, good so far. All right, everybody. I hope that was helpful, and as always, best of luck. Take care.